LUKSO as a blockchain for the new digital lifestyle space, how we call it. It's an EVM chain, but focused on more social blockchain apps. You know, more like fashion, more interesting like use cases and applications for women, for the social media crowd, for the 1 billion people on Instagram. I mean, we have a lot of ideas and we have a lot of contacts within the lifestyle space. And we want to initiate this network creating, I mean, I don't want to go too deep into whatever LUKSO is right now, but, and I just didn't want to make just an ICO, you know, smart contract here, Ether in their tokens out, because I have proposed ERC20, and I think with my background in the Ethereum community, I have to do a bit more than just, you know, making a random ICO. So that's the gist behind it. And why do I came up with this idea of like the reversible ICO, actually more than 1 year ago, when I heard about the rICO, so the DAO ICO idea from Vitalik. The problem with this is, you know, the idea was, okay, people give money over time and they can vote to put this in a refund state. If the project is scammy, they can vote on milestones to increase the tab or decrease the tab. This is a good idea, but as we have learned with the DAO, people don't vote, especially when there's no interfaces which allow you to vote easily. So my idea, I do believe very much in the wisdom of the crowd. I think people, especially as a community, act always more right than one single person alone. And the idea of the rICO is actually give control back to investors. And in simple terms, it's basically people putting Ether in a smart contract, but it's instantly, they basically reserve a certain amount of token. So first I go in, it's get put in a pending state because we have to do whitelisting. We have to approve the KYC information. The moment they get whitelisted, they get the tokens assigned to their wallets. So now they see the full balance. Let's say they have bought 1,000 LUKS. They see the 1,000 LUKS, but they can't move them because they haven't bought them yet. They basically see a balance they can't move. And that's called a locked token and an unlocked token balance. And what happens now is basically over the period of the rICO, let's say it's 8 months, you are buying those tokens up completely linear. So after 4 months, you have bought half of them. After 6 months, you have bought 75% of them, and so on. The ones you have bought, you can move them freely around. That works in a way that the token contract simply checks what is still your locked balance, and everything else must be unlocked. So even if you move extra tokens on this address, you know, it doesn't matter because it only checks for what you cannot move instead of what you can move. And basically what happens here is you just buy our tokens over time. What you can do is with the reserve tokens, which are locked, you can send them back to the rICO and you can get your Ether, your corresponding Ether out. So basically you can reverse your decision. And because you can reverse your decision at any point in time, it activates the wisdom of the crowd. So let's say LUKSO gets scammy and we want to run with the money. You know, somebody will realize, okay, LUKSO is not working anymore. I saw them here driving a Ferrari, you know, obviously this is scammy, blah, blah, blah. So then, you know, this will make the round in the crypto community and every investor could easily get out. And the way of how it works, you simply send back your tokens. That means even with a standard smartphone wallet where you have your tokens on it, you just simply have to send them back to the same address where it came from. That should be the only voting interface you have in a way, right? There's one specificity, which is when you come in later in the rICO. So let's say you come in into months 3 out, or let's say months 4 out of 8, your rICO period of where you buy your tokens is obviously only 4 months long. That means you buy over 4 months from 0% to 100%, because the end date is equal for everybody.
Yeah, Cheyenne, like the rICO is supposed to be over 12 months, the total period of time.
I mean, right now we would set it on 8 months. So we actually changed.
Okay.
So in fact, it is 9 months because there's 2 phases. There's the first month, which we call a commit phase. And there's the rest of the period, which we call the buy phase. Why is there a commit phase? Because the point is, we basically want to have 1 month where people can allocate themselves, like reserve tokens, where there's no risk. So in the commit phase, which is the stage 0 in the whole process, there's just no buying happening from the users. Means you can go in and out as much as you wish. You lose nothing. So you can reserve some tokens. The next day you can decide different. Can go out again. The only thing you pay is gas. Only from month 1 on we start buying. So the whole first commit phase is only there that this whole FOMO thing goes away. People can go in, reserve their spot, but they can also have a second thought, and decide, okay, that was a bad idea. Let me go out. Actually, I need my money, or I didn't really think it was a good idea. I didn't read the website, I didn't scroll down. All these things happen quickly, pretty often. So to prevent this, we have this commit phase. And this commit phase could be any time frame. We just make it 1 month long, or we make it 22 days long. These are all parameters.
My next question was about the price, so you already answered.
So there is price increases. Why is there price increases? Because if we wouldn't do that, what happens is everybody just waits until last month. Why would you go in if it's the same price for everybody? You just wait until the thing looks like it's almost full, and then you just rush in, which defeats the whole point. So if there's an advantage of getting in early, you want to get in early, right? So because otherwise the project doesn't get any money over the period of time, and then the whole point is like useless. Okay, so basically I'm in the Reversible ICO, LUKSO network, Reversible ICO smart contracts. I'm in the audit branch. And what we have here mainly, what is the most relevant is in contracts, the Reversible ICO and the rICO token. The rICO token is a simple 777 with the modification that the only thing balance. You will get that information from the rICO contract. So when we deploy, we have to tell him what's your rICO contract, and he has to basically use this as to check whatever is your locked balance, the one you can't move. So the rICO sol, that's the whole heart of the thing. And you can see the code, right?
Yes.
Okay. So basically we start out using 80/20 registry to make sure that the 777 contract can call this contract, and we have the token recipient interface. And then we have 3 variables that make sure that the contract is on the one hand initialized. So there's an initial init function where you set all the initial metrics, and there is some security. I'll explain in a bit. So basically the contract can be frozen. We have to keep track of the frozen period to deduct it from whatever period is after, so that we be treated like that frozen thing never happened. And the free start is used to calculate the frozen period. Here are all the addresses, which is the deploying address. This is the one which can call the init function. We have the token address, which is 77 token. Does my internet work again? So we have the project address, which is LUKSO in this case. This is the one where the money goes to. This is the address that can withdraw any unlocked ether in the rICO. And then we have the whitelisting address, which is an address that can whitelist any participant. Then we have a freezer address, which is the one which can put the contract in a frozen state. That's separate because that might be an address that needs to be called. So the project address might be a multi-sig wallet, while the freezer address has to be able to act quickly. Because if there's something going wrong, we need to be able to freeze it instantly without the big voting times or whatever. And the rescue address is once the smart contract is frozen, the one who can move the funds and the tokens to another address. But he has to wait 3 days before. And this is to a third party, some kind of escrow or lawyer who just keeps care of it until we hopefully never will need to use it. That's exactly why you are here. That we don't even have to use this, and we can remove the freezer address at some point. So then you have a bunch of public variables. So these 4 variables, or 5 in the beginning, they are purely to track the current state of the rICO. So this is mainly used for then the website. So once we want to know what is current token supply. Second, we want to know how much Ether is currently committed. Committed Ether means this is Ether buying tokens. This is untouchable Ether in a way for us, but Ether we potentially can touch once they bought the tokens over time. Pending Ether is all the Ether where we haven't whitelisted the addresses for. So people are able to first put money in and then whitelist themselves. The whole idea is that, you know, the beauty of the ICOs in the past was you just send a transaction and you're part of it, right? And that's got all killed with this whole KYC bullshit, where you now have to do through lengthy processes where like 2 weeks later, you don't even care anymore about whatever you wanted to invest because it was too complicated. If you let people invest first, they have a very high incentive to actually follow through with the whole thing, right? Cancelled Ether. This is all the Ether which, where somebody canceled their pending Ether. We don't really need that. We actually don't really need to keep track of that. Move it, it's just because we can. And withdrawn Ether is all the Ether that any participant has withdrawn. So every time they send back their reverse token as a reserve tokens, they can withdraw their part of Ether, and this is keeping track of all the ever withdrawn Ether. It's in a way also quite a useless variable. It's more for statistics rather than functional. But below that one, the project withdrawn count, that's also statistical, but interesting. How often have we called the withdraw function? But the more important one is actually how much Ether have we withdrawn. That's a very important one, because in order to know how much we can still withdraw, we have to calculate what we have unlocked so far minus what was withdrawn already. You know, otherwise we would withdraw too much. Then we have a min contribution. The min contribution is there so that people can cancel their pending contributions at any point in time. So the way of how you could cancel, let's say you put in 10 Ether and now you think, oh my God, that was so stupid, I need to cancel that. What you could do is, instead of calling the cancel function, you could simply send an Ether amount below this min contribution to the contract and will auto cancel whatever you have pending.
That's I've got to be honest, that's a really smart UX pattern, Fabian.
Yeah,
So that's really cool.
So the initial idea was actually that everything works with a pure simple wallet. We do, and this does, we do though have chosen to not allow people to contribute by simply sending Ether. They have to call the commit function. They have to put in the data field the commit function, 4 bytes, because that actually makes sure that they will not send it from an exchange. And that they at least are able to, that they have a wallet where they can enter data, you know, because that makes sure they are able to move their tokens in the worst case, you know. But obviously getting out should be as simple as making a 0 value transaction. Because some wallets don't allow 0 value transactions, you can have a simple low value transaction, and that gives you a pending Ether out. The next thing is basically how many stages you have, or the mapping for the stages. I have put that in the reverse way. The actual structs are defined below to make this whole thing better viewable. Otherwise it gets very messy, structs there. So all the public variables are on the top, and then everything which is kind of, you know, more hidden goes on the bottom. So how much blocks are in each stage, and we have the stage count. Stage 0 is a special stage because it's the commit phase. So stage 0 could be different from stage 1 to X. Then we have a struct for the participants. That's actually very important. It's simply address for participant. We have this address, this participant by ID. So this is a simple counter, you know, 1, 2, 3, 4, 5, 6, 7. Each one gets its own ID. The question is, do we really need this? That would be interesting if you want to iterate over all participants. You know, you have to have a way to go through with a for loop. the question, do we need this or not? You know, it's a simple struct. It's just there. And we have a participant count. Then we have the metrics for the commit phase. Basically, what is the commit phase price? What's the initial price? When does the commit phase start, which is the whole start of the rICO itself? When does it end? And how many blocks does this phase have? And then the same for each, for the buy phases together, which is basically when does the buy phase start? When does the buy phase ends? And how many blocks on the buy phase? The buy phase is basically stage 1 to X. That could be many stages. We do need very often the buy phase end block because we need to know when the whole thing's over. So basically it starts with the start block and it ends with the end block. Here, that's the two things. Then we have internal variables about the currently project reserved ether and the last block. Since we calculated this, they are internal because they are not up to date when you want to call them. They are only the last state since we calculated it. And I will show you that in a bit. So yeah, down where we have the structs. So the stage is simply start and end block, token price. This is not really used for anything except for that, you know, you could read from the rICO and you know when the whole thing's, when each stage starts, can do calculations. More important is the participant struct, because here you have is the guy whitelisted. So each participant is one address that participated. So is the address whitelisted? How many contributions does it do? That's purely statistical. How much withdrawals that it has done is purely statistical. The total reserve tokens, the total committed ether. If there's any pending ether, means he hasn't been whitelisted yet. And current reserve tokens is part of the calculation, very important, and unlocked tokens, but that's more statistical too. And again, it has the last block. So same thing like the project. Each participant has a last block, since when he calculated the last time, whatever he has to get. And then each one has a mapping with their stages. And in each stage, we have a pending ether variable, because if you have contributions over multiple stages, it could be that you contributed 5 times over 5 different stages, or twice over one stage and then 3 times over 3 other stages. We need to accumulate the amount of ether in that stage so we can give you the correct price the moment you get whitelisted. Because then we have to basically convert that pending ether at that stage in whatever tokens you get. That's why we need to keep track of the stage stuff here. So then we have basically 2 main events, and I'm not sure if this is something we will improve in the future. It's also rather irrelevant for the audit, but we have application events, and then we gave it IDs like contribution added, contribution canceled, contribution accepted, whitelist approved, rejected, and the project withdrawn. This is just application events. Same for transfer events. If we do this way, you know that you have one event with different enums, or if we do it, you know, in different events, I have to see. That's how initially Mickey wrote it. And then all the rICO already starts. Is this clear so far? Any questions concerning the variable thing? Pretty straightforward.
Yeah, I got a few comments that popped up to mind, and I was like just writing some things. The first is that I think it will be harder to get listed, for example, on Uniswap with an ERC 777, because they need to make sure that I'm sure this will be. They promised us when we did the audit that they would put re-entrancy mutexes on their V2. So I don't know how this is going to end up being in V2. I'm sure it'll be okay. But for V1, I think it's harder to list 777s on Uniswap, if not at all impossible. So that's the first thing.
Okay, that's a good point, but the 777 is ERC20 compatible. So it has the same functions too.
I know, but the problem is with the callback function. when you transfer, you can always call back from that contract, and you could set up something so that the token was malicious, right? I'm not saying that it is the case, and that's why I'm saying it's more difficult to get listed in their website, but I'm sure Hayden or someone from the Uniswap team would have to see the audit for the token first or something like that. So maybe after we do the audit, they can list it based on that assumption. I'm just saying that it'll be harder.
Okay,
and
yeah, so the thing is, yeah, I mean, first off, we are using Open Zeppelin ERC 777. It's 100% Open Zeppelin. We probably should check if there's an update in the Open 777 contract, and we just do some minor modifications. That should be very easy to check.
Yeah, I think it's fine either way. After we do the audit,
it has to be a 77, or at least, I mean, we could also have made an ERC 20, you know, which does a custom call. But in order to be able to send back the tokens to the contract with one transaction, you need to be able to send it to our contract. So then it will be the token receive function.
We'll make sure. We'll make sure to include something about decentralized exchanges in there. Make sure that like people feel safe listing the token. We'll make sure to include that.
That would be good.
Yeah. Another thing that jumped to mind was that maybe the state variables for accounting that you showed us, maybe they're not needed. Maybe they could just be getters, right? And you do the math when people call the function instead of saving it in the state.
Yeah, so that's a bit of a tricky part. So actually all the variables up here, so there is some you need to keep track of, and especially the withdrawn ether. This is very important, and these internal ones, they are very important. And you will get to this here. Here, the currently reserved. The current unlocked, not so much. That's more for viewable, and that's why I made them internal, because people shouldn't read them and think they are actually valid. This is actually already solved through getters, and these. So you would. It's not complicated, but there are some specificities to that. So
cool. Yeah, let's just go on. Sorry that I interrupted.
Yeah, no problem. It's probably also good. By the way, let me just get. How is your name again? Not Gonzalo. Cheyenne. Okay. Now I couldn't see it. Cheyenne. Okay, now I can see it for whatever reason. Okay, cool. Yeah, just want to make sure that you guys are clear about it. So we have basically here the constructor. The constructor does nothing else than saying deployer address message sender, and we're setting the interface implementer so that this contract can be checked if he supports ERC 777, and he does after doing that. So then we have the whitelist, the init functions, and the init function basically is exactly where you set the token address, you set the whitelisting address, the guy who can whitelist, the project address, you set the commit phase start block, which is basically the whole rICO start. You set the commit phase block count and the commit phase price, which is the rICO initial price. You set how much stages it should have on top of the commit phase. So you would say 8 stages for 8 months instead of 9, because the commit. And you would say how much each stage should have as blocks. So you could say commit phase is 22 days, and you could say this each phase after is 1 month, 31 days or whatever. And how much the price has to increase per each stage, which already will be valid for the first month, for the first stage. This can be only called by deploying address, and it can only be called if it's not initialized. And it cannot be called, obviously, if the rICO already started. So the commit phase cannot be before it's initialized. So basically what we do here, which is simply we have set the project freeze and rescue address to the same address. This is simply for simplicity. On the end, we will add this up here, but then I need to change a bunch of tests too. But yeah, the freezer address, rescue address, project address obviously should be very different addresses. This is really just to simplify it right now in the tests. And then here it does nothing else, and it sets the commit phase start block. It sets all the variables you set. There's some special thing when we talk about the end block. You basically take the start block plus the block count, but you have to deduct 1, because if you say the thing is 10 blocks long and you're starting at block 11, then you would end up at block 21. But to get the last block of this thing, you have to go 1 back, because it should end up at 20. So the last block of this period would be 20, because 21 would be then already the start block of the next one. That's why we have to subtract 1 here. And then the whole thing basically just sets the commit phrase, and it iterates over each stage count and does the same thing for each stage. And on the end, it calculates the end block for the buy phase. It calculates the full duration, and it sets the initialize to true. So that's all what's happening here. Setting the variable, setting the addresses, and setting the rICO frame. So then we have the public functions, and the public functions are basically the only ones really where people can interact with. These are all state changing functions. These are the real interface of the rICO. Interface number 1 is the fallback function. In this case, you can't contribute anymore, which we could have done, but you know how people are. People are, if they can make mistakes, they will make mistakes. So I think it's not smart to let them do mistakes. So sadly, we had to remove the contribution, the commit function from here, because I think it's just a problem. You know, we will save so much hassle by not allowing. I mean, I really wanted people to just send Ether here, but you know how it is. There will be definitely that guy who sends it from an exchange, even though you write in fat letters, not send from exchanges. This way, they at least cannot send from exchanges, because the thing will be simply canceling. So what it does is it checks if the value is below the min contribution, and if so, it cancels whatever pending contributions you have. So basically, this is only to cancel. This next one is the token receive function, and that's the one which is called from a 777 token contract. So what it does is, first we check if the contract is initialized, which we, I think, do check on every function of the external ones. And it checks that the contract is not frozen. Same with the external, the fallback function. So if it's frozen, you can't do any of those things. You can't contribute, you can't cancel, you can't do, no money can go in and out, because that would be problematic. So what the token fallback function is, this will only be called if there's a token sending tokens to this contract. So we first check if the token address from which the token came is actually our known rICO token. Otherwise, we just fail the thing. And then there's 2 things that can happen. Either the project sends tokens, then it could increase the token supply. So let's say, for example, LUKSO is going well, and you know the 20 million LUKSO are bought up, and we think, oh my God, let's just sell another 10. Why not? Because we haven't fixed the selling in the public ICO so far, 20%. We could put whatever 5 million more, and this should be instantly working. It should technically be no problem in the whole math. Actually, this is not really heavily tested though. And the other thing is, if it's not coming from the project address, if not the project address is sending you tokens, then it's automatically withdrawn. So it assumes that a participant is sending his reserved tokens back. And then it calls the withdraw function. And the withdraw function is basically when a participant wants to get his money out. Then there is...
sorry for me, my mind got stuck somewhere, and I'm like trying to like figure it out to follow you. So one thing about the fallback function you mentioned, it's so you want to prevent anyone to like call, like just send directly Ether to this contract, right?
So the initial idea, so the initial idea was basically the people to contribute to the rICO that send Ether to the rICO. Mm-hmm. But if you do it like this, you know, people can send from exchanges, people can send from wallets that are incompatible to hold ERC20 tokens, and they would be stuck, you know, because if they cannot move the tokens in the wallet they have a problem.
So my question is, how does this stop that from happening?
Because the
It's just like because
value has to
because of the
be
require it should oh okay I see.
Yeah, because
So
of the
the cancel yeah okay
yeah.
Never
So
mind.
basically, you just can't send any ether, which are higher beside than the min contribution.
Yeah, thanks. Mine was kind of stuck there.
Yeah. So what you have to do is you have to call the commit function, which is line 354. So basically, there's two ways to interact with the rICO. One is send your token back that we'll call the withdraw function, or the other, send ether and give in the data field the commit function name, which is simply here in our random test. What is the thing? Right here. This send this data field. We will write this on the website. Hey, here, put in your data field this text, and that will basically commit. This simply calls the commit function. But at least this time, this way, we are definitely sure that a user wallet that has data field input in it, which makes this whole thing a lot safer to contribute. So what the commit function does is a bit more complex. Again, it checks if it's not frozen and if the rICO is running. We're not doing this rICO is running check here in the tokens received because we have to be able to send tokens to it before the rICO starts, obviously. You know, if there's no tokens in the rICO, you can't even sell anything. So again, if it's running. So you can't obviously withdraw before the thing started. So what happened here is, here we do exactly the opposite. You have to be above the min contribution. We are creating a new participant record in participants message sender. We are creating a new participant stage record in the current stage. This is where we check if the participant is basically not yet existing, or if it's existing, we check if there's zero contributions. If there's zero contributions, then the guy definitely hasn't done a contribution, so he's new. In this case, we create this IT counter thing, which we don't use right now, but it could be useful to iterate over all participants. Maybe in an interface or whatever, you want to maybe make a way to, maybe you want to display all contributions in a website or whatever. You need to know, you need to be able to get this participant per ID. We increase his contribution, take one. We put the pending ether and add the value, whatever he sent. And you know, we have to note that he has to send something at least higher than the min contribution. And for this specific state, we also set the same amount of pending ether, because in this stage, he paid a certain price, right? And we also increase the global pending ether variable and add the same amount. Then we fire the event. And then on the end, if he would be already whitelisted, for whatever reason, we whitelisted him before he does the first contribution, can also happen, then we accept his contribution. So we could now make two functions, you know, one for instant accepting and one for later accepting, but this, I tried that. The gas saving would be, right now you would spend around 150,000 gas for doing a contribution. The gas saving would be, no, 180,000 gas, sorry. The gas saving would be 40,000 gas, but we would double the code. We would, I mean, have twice the same thing, which almost does the same calls, and we don't really win that way. So we just have one and does it also later. So if you're not whitelisted, basically you will stay as a pending contribution. If you are whitelisted, it will process instantly this pending contribution. So, and that's further down in the internal functions. So the second thing is the cancel function. That's simply for people who, you know, instead of, you could send like lower than amount, but you could also send just call the cancel function. You know, that's just a convenience function. It does the same thing. It calls the cancel pending contributions.
Well, but it only cancels part of it. Whereas if I send the other one, it'll cancel all my tokens, right?
No, this would cancel everything. Canceling means always getting everything out.
Okay.
So it cancels all your contributions.
Okay.
Both of them cancel everything. It's just two different ways to get to the same thing. Here, this is for the guys who don't know how to use a computer. And that's for the guy who has a fancy interface, a fancy blockchain interface, you know. You can call the cancel function. They both do the same thing. And they have this message value, just that we refund whatever they are sending us extra, you know, that they get the money back.
Oh, okay, I got it.
This is really just, if people are stupid enough to send us extra ether in this, they get it back. We have to refund them. Then we're getting already to the functions which only call. This is the whitelist function. So the whitelist function basically just approves whatever pending ether you have, or rejects and cancels your pending ether. That's all it does. And basically what we do is we have an address, we have an array of addresses, we could give multiple addresses, and we have just, you know, all these addresses get approved, true, or they get rejected, false. So what it does is first it checks if you have given any address in the first place. And if not, we basically iterate over all addresses you have given. We get the participant address because it looks nicer.
Sorry, Fabian, sorry.
Yeah.
Is there any reason why this function is only when the rICO is running?
Yeah, because would you be able to, I mean, nobody can contribute after, and if the rICO is over, we wouldn't whitelist anybody anymore.
Right. I was thinking maybe before, maybe if you want to whitelist people before.
So the thing is, you could cancel. You can I think you cannot even you could cancel after the rICO is over. I think. Let me.
Yeah. Okay. Sorry, I don't want to distract you from your flow. Let's go through the code. Sorry. I actually prefer if we go through the code.
Yeah. Let me just quickly check if. So yeah. So you can actually cancel even after the rICO is over, because obviously it could be that you have still a running, you know, you have a pending contribution. You just never really bothered like doing anything. We will have a mechanism that we will refund inactivity. If they haven't done their KYC, we will refund them. But it could be that somebody contributes exactly 1 week before the end. He still should be able to get his money back, because if we can't whitelist him after, the guy would never get his money out.
Yeah.
That should not be a problem. Actually, the math completely still work fine. So basically what happens here is we go over all addresses, and we simply do, if this is for a whitelisting process, he just checks if the guy is already, if he's not whitelisted, set his whitelist status to true, emit an event, and accept pending contributions. In any case, I mean, if he's already whitelisted, he shouldn't have any pending contributions, but should this ever be possible, which I don't think is possible, at least, you know, he can still, you know, this will still accept his pending contributions. In the other case, if we send false and we want to reject him, we simply set his whitelist to false, we emit the event, and we call again cancel pending contributions, which in this case, we send 0 value with it because he didn't send any, he didn't call the cancel function or the fallback function. So there's nothing he will get back. That will simply cancel his contributions. So that we use this even for when we cancel people, even we don't reject them officially, because everybody is by default whitelisted false. So everybody's whitelisted false in any case. But this is the way of how the project could also cancel somebody's contribution. I mean, we could user X, but calling whitelist, you know, false is doing exactly the same thing. So except that we will emit one event saying he was rejected, which is not really true because we just canceled him, but it doesn't matter. So what the whitelist does, it's purely enabling an address to accept contributions automatically, or to reject or put them into a pending state, the contributions. The whitelist, if we call whitelisting false contributions, it will not cancel his already existing contributions or does anything with his existing. So once he got in, he got in. We cannot we could program this, but I don't think it makes any sense to basically auto refund his reserve tokens or whatever. So once you got in, you got your contributions accepted. If we would, for whatever reason, reject him later. The only thing what we do is we prevent him from making more new contributions, but he will get to keep and be able to withdraw or, you know, reverse his whatever previous contributions. Because the only place where this whitelist thing is used is exactly in this point up here, where it's auto accepting the pending. So when you contribute and you commit, it will just auto accept your contributions. And the only other place where we accept contributions is if we approve his address. That's the only two places where he could ever accept contributions. So either he has it already on whitelist true, or we whitelist him. So next up is the project withdraw function. That's how we get the money out of the pot. We only can call this function. Then the thing has to be initialized and the thing cannot be frozen. And this is a surprisingly simple function because we do nothing else than we calculate the project allocation. This will update the project unlocked ether variable to the latest unlocked amount of ether we have. We subtract whatever we got before out already. That gives us the available for withdraw. This has to be obviously more than from whatever we wanted to withdraw. So we have this ether amount, which we can give it. So we can only get a part of the pot out or everything. And then it just increases the withdraw count. It adds the withdrawn ether to this global variable, and it sends us the ether to the address. That's all it does. So this does basically nothing else than calculating the amount before. So magic is happening here, and it takes this variable minus what we withdrawn, and that's what we know we can get. So these functions, the next functions are the security escape hatch functions. So we have a freezing thing. This can be only called by the freezer. It remembers the current block number when the freeze is starting. Is there any questions so far, by the way, or should I wait? Okay. So freeze function basically just puts the thing in frozen true. If frozen is true, nothing anymore works, no in, no out. And we use the get current block number. Why we use the get current block number instead of block.number? It's because we need to be able to modify. I mean, for testing, it's really useful. And we also need to be able to modify the current block number in the moment there was already a previous frozen period. Frozen period from the block number. But in this case, freezing is simply, you know, setting the thing to true. Unfreezing is setting it to false. And what we do is we basically calculate the frozen period, which is frozen period, and we add whatever was the period was frozen since the last freeze start. The freeze start is basically next time reset again. So then we have this disable escape hatch, which only a freezer address can call. So in the case we feel super confident that the rICO is working well, we can just simply set the rescuer and freezer address to 0. Nobody can, you know, save that guy anymore. And the super escape trap, the super security hole in this whole thing is somebody, in this case, the rescue address, which will sit in a safe box, could, if the contract is frozen, that means it requires us to freeze it first, could send all of this money and the token to an address. Idea is, should anything happen, we can freeze the contract, we can discuss what needs to be done. Should we upgrade this thing? Should we send it to a refund contract, whatever? And in accordance with the lawyer's agreement, we can do that, but only after 1,800 blocks or 18,000 blocks, sorry. So that's roughly 3 days.
Wow, really? They agreed to that? I'm gonna be honest. Seeing this makes me a little bit nervous. Makes the security professionally me nervous. Just because this means that there's one private key that manages the whole thing, right? So the key management has to be super tight.
But not really. You need to freeze it first, and then you need another key. So at least 2 keys.
So it needs 2 keys at least.
Oh, two keys, right? You need
so
two
you
keys.
need at least the guy to freeze it first, and then wait 3 days, and then the rescuer can call this function. So the thing is, I would love to not have it, but I think we would be completely stupid to not have it. I mean, as much as I hope, I mean, I'm pretty convinced that the rICO is pretty secure. I mean, it's the first of its kind, you know, and having the security measurement in the first ever version, I mean, once it's running once we know it's safe, once you guys audit and tell me here, this is the like super tight, and we all feel confident, we can call the escape hatch disable function, the next iteration we can remove it. But not
would
having
you consider,
would be bad.
would you consider, we'll have time to talk about this over the next 2 weeks, but would you consider doing something like enabling people to withdraw during the escape hatch period?
Yeah, so the problem is, what is if the bug is exactly in the withdraw function? You know, the whole idea is that you want to prevent any movement, whatever, because we don't know where, you know, maybe the withdraw function, in fact, is the most complex one. The likelihood that if something goes wrong, it's going on wrong there is high. So yeah, that would be probably the worst of all the.
And to be fair, I really like this pattern more than upgradability. So.
Yeah, no, I don't like upgradability. I think this is much better than making it upgradable. I like this much
you
more.
have the disable.
And the thing is, exactly, so if you want to make it upgradable, it is straightforward. What we can do is we can simply say we deploy the thing again, we put everything the way it was, we transfer all the ether and the tokens to the new contract and continue from there, right? And it's easy. I mean, it is really easy, and I'm not sure if I mean, you tell me if there's something here potentially dangerous, but the idea is that the rescue address will sit with a legal entity. I mean, you can also tell me if you want to keep that key, you know? I mean, somebody has to keep the third-party key. It cannot be us, you know? Because if we have both keys, we obviously have full access to the rICO. That defeats the point. So we do want this to be a third-party person, and ideally it's not even a person who is not knowledgeable. I mean, you can have that key, or one of our lawyers will have it. I mean,
I think one thing that would make this better would be if instead of a parameter in the parameter 2, if you have it in the initialize function. So it's known at deployment time that you guys cannot just, that the rescuer cannot just like flee with the money to the Philippines.
To the Philippines. So, I mean, the thing I thought about it, actually, initially I had no 2 here. I had the project wallet address as the fixed address. But the thing is, I mean, you could just make a very nice instant continuation, because you could send it to the next iteration, which we don't know yet what that address is. The upgrade, we could send it to a refund contract. We can't determine right now what the refund contract is. Otherwise, we have to send it to another address, which now we have to trust. This way, you know, the thing is frozen. 3 days, nobody can do anything. So even if an attacker gets both keys, however, you know, he breaks into the lawyer's office and then he punches me in the face and gets the freezer address somehow, then he still has to wait 3 days to do anything, where we send law enforcement and shoot him down. No, you know, so before you can do anything. So there's that.
I'll think about this.
Yeah, write up on like the possibilities and like what could be like suggestion and like counter suggestion. So it looks good so far. Like, on the report.
It's definitely to be I mean, it's easy to change that, right? So, but the question is, I think the question is that the rescuer address will only be agreeing to this if they think this is a safe way to go forward, you know. I mean, in ideal sense, that never even is a problem, these 5 functions here, and never be called ever. So what we have after this is the public view functions, and this is basically all the functions that are either relevant to do calculations. Actually, in this case, yeah, they're relevant they're mainly relevant for interfaces. Here, for example, we have the get unlocked project ether. That tells us exactly how much ether were unlocked so far by this point in time. and we have the get available project ether is the same thing minus what we have withdrawn. So that tells us how much we can get. This tells us how much was unlocked so far, no matter what we took from it already. And this kind of already contains one of the secret sauce of the rICO calculations, which is the heartbeat of the rICO. It's called calculate the unlocked amount for your current project reserved ether. And you give it the project's last block. So that function, I will get to it, is the one which is used for everybody. Participants and the project uses this function to calculate the ratio of what they have. And why calculate it this way? Why is there the last project ether? I need to show you. I guess I will just draw it. So in order to make the rICO happen, and this is a little bit of a mind bend, and you know, I can tell you, it took us quite a lot to get there. And on the end, Marja and I were sitting like there manually calculating it for one participant through to really understand the fucking whole like complication. But the thing is, if you have time, oh sorry, you don't see my, here. You see that? Yeah, maybe a little video here. So that's the axis time, you know, something will happen. Problem is, let's say I have 5 ether or 5 token bought, and then I go out at some point. So I have only 4, then I stay a little bit, and then I go in again and have 6, and so on, you know, and I can do this. So imagine my contribution pattern is like this. Mm-hmm. I cannot simply calculate, hey, how much I have right now? I have 5 again here.
Right, because you already paid some before.
Yeah, so I cannot simply calculate how much I should have unlocked until this point in time, starting from the beginning. There was some parts which I got where I got more because I had this much. So basically it will look, if you look at it, it will look a little bit like this. So it will look a little bit what you get looks a little bit like this. Because if you have more, you get obviously more tokens unlocked faster. If you have less in there, it will like put the curve a little down. And when you have more in, it gets faster again. So what you have to do is you have to basically calculate every single time there's an action happening, either withdrawing or contribution. You have to calculate how much got into, how much you have by this point in time. And what you do is you, before you give him the money back, you calculate from this point in time to this point in time. And then you know how much you got unlocked. Then you withdraw, you calculate how much you should get back, and then you give him this back, and you reduce the currently reserved token amount by this much token you took out. And when you get next time calculate, you don't calculate from the beginning, you simply calculate from the last block you did the calculation. Now only you have to calculate what is this piece he got, and you add it to what he got before. And then the next time when you add something, you first calculate, I mean, then you can add something. When you first next time calculate, you basically say, what is you got since this point in time to this point? And add this to the 2 previous ones. So basically, that's why we have this currently reserved tokens. So instead of calculating actually this part, the unlocked tokens, we calculate what is still reserved. Why we do that? Because he could have something unlocked and move more unlocked token to his address. So we can never really know what his balance, if its balance is correct, but we definitely know what is unlocked at this point in time. So we actually calculate the upper part, not the lower part.
Okay.
But that's why you have the last block. Basically, you simply always calculate the space since the last time he did something. And that you just add to the currently reserved tokens. And then you know exactly what he has right now unlocked.
That means that, but during the rICO, I cannot buy unlocked tokens from anyone else though.
No,
can I?
No, you cannot buy unlocked tokens because they cannot even move it. So
right, yeah. So I heard you say that. So in what situation would I be able to deposit more unlocked tokens? in there?
When you send more ether to rICO, I mean, you get always more unlocked.
Oh, you're saying that I can send more ethers, so like
you can buy more from the rICO.
I just commit more and like the
yeah. So in that point in time, you would actually send back part of your reserve token or all of them, whatever. In this case, part, because you have still like this much more unlocked. You would basically send back reserve tokens, get ether out. Then you keep it for a while, and then you actually send more ether in the rICO and you buy more. So your reserve token balance instantly increases. So we have to basically always calculate these periods. So that's exactly why these state variables, which you said, are so important, because we have to know what was done, what calculation was done until the last point. So we only have to always calculate only the next. So basically, from the last point we did calculations to now.
Yeah,
we never
got it.
At the beginning of time. That's why we have this. So that's why we have the project last block here. Sorry. Yeah. You see my screen still, right?
Yeah.
So that's why we have the project last block for the project, the same for the participants. So this calculate unlocked amount is extremely relevant for all parties, and they always have to provide the last block. And that's a little bit the tricky part, you know, and I tell you, it took us a while to get to this math, even though it's totally simply once you figured it out. But because the problem is the following, you know, if you want to calculate from the beginning to here, then basically you have things like where he took money out here. Basically, I mean, before the rICO was a bit different. Before the idea was when you get in here, you instantly allocate for everything here. But then he already got here a certain part which you would need to deduct, so it gets really complicated. So that's why this step-by-step actually works really well. And that's what's done here in the get unlocked ether. This is only a view function, so this is not like really changing any state. So this will always calculate from the last point where somebody calculated the project allocation to now. So the other important function, which is also a view function, is the get participants reserved token. So this is kind of the opposite of the get the unlocked project ether. Here, we can basically calculate what is the current reserve token state of a participant. And what it does is it basically takes the current reserve token from a participant and uses the same function again. It takes the current reserve tokens, calculates what is unlocked from this with the last block since this participant calculates something, and we subtract it from the current reserve tokens in order to not get the unlocked token, but get the still reserved tokens. We just reverse this, because that function calculates me the unlocked amount from this tokens. So to get the reverse, we simply subtract it from the same variable. So we keep track for the participant. We keep track of what is still reserved for him. For the project, we keep track of what he has unlocked. And we also keep track of we keep track of the reserve token as well. So we only have to always from the reserve token. So this is exactly this. So this here is his reserve token amount, you know, and from this we need to know how much he still has reserved, because he gives always pieces away over time. I hope that this is not complicating it too much.
And one question, just clarify that lock tokens and reserve tokens are the same? Or
no,
like it's just
yes, it is. Sorry, it is the same. Yeah, lock tokens and reserve token is the same. Unlock token. So what you have bought is unlocked, and what is so we use in the rICO, we use basically lock tokens and reserve tokens. Sorry, unlock tokens and reserve tokens.
Yeah, that was the confusion, because even in the comments you say like lock tokens.
So unlocked is basically the one you bought, and locked is what is still reserved. But I think reserve tokens makes it more clear, because unlocked locked, that makes it even more messy.
Yeah, no, so, just want to be clear.
So we went over a few iterations of naming, but I hope so there's just reserved tokens or reserved ether, and there's an unlocked ether for the project or unlocked tokens for the user. Basically, that's the whole thing. Let me just quickly check. All right, so next one, the get participant unlock token is exactly the reverse function from this one. And this basically does exactly the same thing, with the difference is that it's basically adding whatever you calculate to the unlock tokens. Instead of this, is deducting from the reserve tokens to get the current state of reserve tokens. That's the same thing as you see, just a little bit. There's an add and there's a sub. But this function is actually not really used anywhere, because if you would use, this is only done for testing. I'm not sure if it's used in the contract anywhere, because if you check this against the balance in the rICO, you could have more unlocked tokens than this gives you back, because this calculates your unlocked token amount based on whatever you put in the rICO, but you could always have got some unlocked token from other people, buy it on an exchange or whatever. That's why the way of how the rICO token contract makes sure what is yours, it doesn't calculate what is your unlocked amount. It tells you which amount of your token balance is still locked, also still reserved. What is the part you can't move? Because that one can never increase or decrease except you buy more from the rICO, right? You can't move it, so it's locked. So this is more a view function, and you will be able to, you can simply search where these functions are used, and you will see they're not used anywhere except in some tests. But this one is very important. Get your participant reserve tokens. So the other functions are basically simple things like get the current stage ID. So what stage we are in the current block, get the current price in the stage, get the price at a certain block number, get the price at a certain stage number, get the stage at a certain block number. This is all fairly standard things. Here I put in to do check math because I haven't fully looked into how we calculate if you're in this or that stage, but it should be fairly easy to do. I think it's correct because our tests will all work out, but this is really just checking if you're within some certain stage or not. Committable ether at stage, that's important because that tells you when we are processing pending ether, we obviously have to check if he has 100 ether pending, but almost all tokens are bought up. We have to check how much are these tokens worth at the current price. We have to know how much are still available to be bought, right? Because obviously, if there's only 80 ether and tokens be buyable right now, we have to refund him the rest. We have to only buy him 80 ether in tokens, and the rest we have to put him back. So that's what it basically does. It gets the ether amount for tokens at the stage. It checks the current token balance address. So basically the address of this rICO, which could increase over time, sees how many ether is still at this current price available. And the stage ID in this case is obviously whatever stage you commit. That should be, let me just quickly check, should be actually the current stage at all times. Yes, correct. Okay, good.
Yeah, that one is, the next one is pretty self-explanatory.
All right, so the next one is get the amount of token for stage. You know, this is kind of like a bit of the tricky part where, you know, when you have calculations, in this case, the token price, first we multiply the ether amount to the power of 18 and then divide it by the token price. So the token price is actually not one way of the token in ether, it is one full token. So the way price represents one full lux. That's why here in the calculation it's always to the power of 18 before the price is calculated. Same for if you want to get the ether, it's doing the same thing, just dividing it by the power of 18. That's to prevent, basically to allow that each, that one way buys at least one fraction of a token. But the ether price, and that's important, sorry, the stage prices, or the stage price is always the price of one full lux. It's not a way of a lux. So then we have the super important function, the get current block number. And this is kind of where a little bit of a magic is happening, because we subtract the frozen period, if there should be ever a frozen period. It's getting, and this actually magically works out all the other functions. Basically, if you unfreeze, it just, for the rICO, it's, even though we moved like 50 blocks in the future, for the rICO, it behaves like no time has passed since the thing, like during which it was frozen. Which is also important because you don't want that we keep it frozen now for like the rest of the rICO, you know, nobody can refund anymore. And so in a way, if you want to have calculate the proper future ending, you have to add obviously the frozen period. But this get current block number solves that. There's one other place where this is used. Here, get stage at block. So when you get the current block stage, it obviously needs to account for the frozen periods being a different one. So this is now the magic comes at line 722. This is the heart of the rICO. This is the whole magic, man, which took us fucking forever to figure out in concert with the other shit. So, but this is, you calculate the unlocked amount of ether, and what you give it whatever amount of something, either ether or lux, and you give it the last block, and since when you want to do the calculation. And what it does, it returns you what is unlocked of that amount by now, since the last time there was a calculation. So we're getting the current block. If the amount is 0, obviously you get 0 back. You know, there's no point in calculating 0 against 0. And there's basically just three things that can happen. Either the rICO is within the biphase, yeah. So only then something is moving from us to the project, or from us to the user. Only in that moment there's anything moving. Or it's after. If it's after, then obviously whatever total amount he's asking will be unlocked. So everything will be unlocked. Or we are before the rICO, and then obviously nothing is unlocked. So the thing will return you 0. And here is a little bit of the magic. I mean, it's not magic really. It's just really just, it calculates basically how much blocks have passed since the last block. And let's say we are in block, let's say this is from 0 to 100 is the whole rICO period. And we have not calculated anything. Then the 0 block, the last block is 0. And if we are now at block 30, then we just simply calculating current block 30 minus 0 is 0 divided by 100 blocks, which is the total duration of the whole rICO. And then we know at this point, 30% of the token amount should be unlocked. So we calculate whatever this amount times past blocks divided by total block count. And we do have to, again, do this multiple to the power of 20 to prevent rounding errors. I guess you have to see that a lot, because you can have floating points calculations. We cannot return a floating point. But basically, it just simply says, what is the percentage of unlocked in this point in time? And if we're starting at the beginning of the biphase, whenever this is, and make this calculation, it should be, for example, 30%. But in order to know, so think of like we have now calculated 30%. And the guy now deducted whatever amount of tokens or ether he got back. So now we keep this 30% calculation fixed. If we now move to block 50, we want to calculate how much we have to now calculate from this point on. So this doesn't start at block 0, it starts at block 30. So if we're now at block 50, we simply calculate the current block 50 minus the 30. So that gives us 20 blocks have passed since the last time we calculated. And the total block count in this case is not the full from 0 to 100, but it's from 0 to 30. So only 70 blocks, because we already accounted for this first 30%. They're already totally calculated. So we keep them as we know about it. So we only calculate now how much is 20 divided by 70. So 20 blocks passed, and the whole rICO duration is only 70% long. So we calculate 20 divided by 30, and then we know how much got unlocked since the last time we calculated. And that's kind of, if you look in the math, this is then really nicely calculating these different increases, right? It would be faster here, but if the thing goes slower, then there was less unlocked because there's less amount of unlocked in this period and more in this and so on and so on. So that's what this does. There's one custom thing here is that if the last block was not set yet, obviously we have to set the last block to the buy phase start block. So if the user never has done anything, the last block is the buy phase start block. We have to deduct 1 because the last block buy phase is already 1 block within the period. In order to make sure that it's definitely before the thing even started, we have to deduct exactly 1. As you probably should use here sub.1 instead, also save math instead of a 1.
It's fine. It's fine because block number will never be 0. That's like a dogmatic. It's true, so it's fine.
Yeah, yeah. So, and this is actually the whole magic is happening exactly in this, and this is equally the same. So this calculates, for example, the unlocked amount of ether for the project. It just treats whatever is in the pot right now. And since I last time calculated what should I have gotten until this point in time, and the same is for the user, how much tokens are unlocked in this point of time, deducted from what I still have reserved. So now my reserved amount goes down. If I now do another action, we calculate again what happened since the last time I withdraw or contributed, how much more I've unlocked until this point in time, deduct it from my currently reserved amount. So now I can either deduct a certain amount or add more, whatever. So basically, the important variables in the whole game are your currently reserved or currently reserved ether amounts. And you always just deduct from that, piece by piece. So then we are moving to the internal functions. These internal functions are simply for sanity checks. For example, we do a sanity check on the project. We basically check if the current committed ether, so what was ever put in the contract minus what was ever taken out, does equal the reserved amount plus the unlocked amount. So whatever was ever reserved, what is currently reserved plus whatever was unlocked should always amount to whatever was put in the contract minus whatever was removed, right? So the committed ether should always be reserved plus unlocked. If that ever is not true, the thing should be failing. And the even more better check is the current ether balance equal the unlocked ether plus the currently reserved ether plus the pending ether and minus whatever was withdrawn. So that's actually already an almost bulletproof check, because here we check all the fucking math against the actual balance of the rICO. And in our test, that actually works out. So I think we're good. So we do a sanity check also for the participant, and there we simply check, is his current reserve tokens, reserve tokens. This is actually not the current reserve balance. So this is the total reserve balance. So it's a little bit the counter thing of the total committed ether. I just removed the word total because I think it's unnecessary. And here we just say it's the total reserve balance, the current reserved plus the unlocked. And that should be the total reserved. Means total reserve, whatever he ever reserved in tokens in this rICO over time. Here, then we have two other important functions. The calculate the allocation of the project, again, using the calculate unlocked amount function, and the calculate allocation for the user, using the get participant unlocked tokens and get participant reserved tokens, which under the hood also use the calculate unlocked amount token function. And they basically do the same thing, just from opposite perspectives. So we basically calculate how much was newly unlocked since the last time that function was called. So it deducts this from the current reserved ether. Then we deduct this from the current reserved ether. We decrease the amount of reserved ether by whatever was newly unlocked. We increase what was unlocked for the project, and we save the last block number. And we actually do a sanity check just in case something shouldn't work out. Is this clear so far, or is anything? Okay. So calculate participation does exactly the same thing. We get the participant, we calculate his unlocked amount, and this has to be in this order because the calculate unlocked amount does use the reserve token function. So we can't just deduct the reserve token before we calculate the unlocked amount. Basically, we calculate the unlocked amount and then calculate the reserved amount, which is just exactly the same thing reversed, and we increase that. So we actually update this function, this value by what is now newly reserved, which already deducts the reserved thing. So that's the same thing, just a little bit distributed over these two functions. And we remember the last block again. And in this case, what this participant does, so the calculate participant allocation, we always have to do before we do any action. So if you look at this chart, if we are here at 0, and now we are moving here and the guy wants to withdraw, we first have to calculate how much he has unlocked and this one before we withdraw. If we now move from here to here, we first have to calculate how much is unlocked before we add his new amount, whatever he wants to buy extra. That's why these functions are always called on the top of each accept contribution or withdraw function. But what we also have to, and this is the whole tricky part here, we also, and you see this in this line, in line 826, we do have to also calculate for the project. Because the project, we need to basically make sure that by this point in time, we also have calculated what the project should have gotten. So in a way, every participant, when he does ever something, he has to calculate for himself and he has to calculate for the project. Because otherwise, whatever the project has unlocked would be completely off, right? If only the project will calculate this, and there's users who go out and go in over time, it would never add up to what the project should have by now. Because we would then go in, oh yeah, I didn't check anything since the last like 5 weeks. Let me see how much I get. And then you would get way more or way less than what you actually should get, right? Probably whatever, something. So the thing would be totally off. Therefore, every time the participant calculates something, and this is obviously not a view function because we're setting variables, we have to make sure we also calculate for the project. And because we do that, the whole thing works out. And we as a project don't have to iterate over 14,000 people and check, you know, let me update for every user what I should have gotten at this point in time or that point in time, because they already do it for us. They basically pay for our calculation in that moment. That saves the whole thing. So this is really these little magic functions is these two calculations and the calculate unlock amount. This is the big magic functions. And then we get already to the whole processes. So now we're coming to the actual main process functions. So basically where things are happening. So we have the cancel pending contributions. This function is either called when you are sending a lower than min contribution to the contract to auto cancel your pending contributions, or when you call the cancel function, or when we are rejecting an address. So if an address has a pending contribution or multiple pending contributions and we reject his whitelist, we call basically whitelist with his address and false, then we'll also cancel his pending contributions. And this function is basically the whole thing from here to here, and it simply takes the participant, it takes the participant's pending ether, checks that they are obviously not 0. So if they are 0, we basically say a fail silently. Why we fail silently? Because we are using this also in the whitelist. So if we want to make unwhitelist the user, for example, if we would revert here, it would also revert that we just unwhitelisted him, right? We want to prevent that. That's why it has to fail silently. But in the case that there is a send value, so there is this function was called within the fallback function or within the cancel function, he sent some ether, we definitely have to return his ether, right? Not that we accumulate his whatever, you know, dust he sent along. So basically what we do then is we go over all stages. Obviously, that as we cannot go back in time, we should only go from the current stage on backwards. Or actually we go only until the current stage, it's forward. And we set all pending ether in the stages to 0. We set the global participants pending ether to 0. We increase the canceled ether amount. We decrease the pending ether amount, which is our global variables. And we send out the participants, like whatever he obviously should get back from his pending ether. We do then run the sanity check for the participant and for the project on the end of the function. If there should be any mismatches, it would fail. So the good thing is that pending ethers are not really part of the pot. They are in the contract, but they're not really part of any calculations. They are basically outside of those calculations because they're just pending. And we have to keep track over them per stage because obviously people can have multiple contributions per stage. Each stage has a different price. We want to make sure that when we accept the contribution, we give them the price they came in, right? So that brings us to exactly this second function, the accept contribution. So that's very similar to the pending contribution because the accept contribution can be called either by calling the commit function and you already are whitelisted, or by the whitelist function where we then call it for the user, which sadly means if users have a lot of contributions pending and we whitelist them, we have to pay for their acceptance, which can go actually up to 600,000 gas per user. So I can show you quickly where this is happening. There's only 2 places where this function is called, and it's once here when we accept the user. So there's a whitelist function. We whitelist him and we call accept contribution, or it's called when the user is committing. So the user, when he's committing, he's creating a pending contribution, and then we check, is he whitelisted? If so, just already process his contribution. That's basically only two places. Same when we look here in the cancel pending contributions, it's called in the whitelist function when we cancel him. So we set it to false, and we call this also just to make sure that whatever is pending will go back to him, or in the cancel, or in the fallback function, which has to be below the min contribution. So the accept contribution and the withdraw function below, these are the 2 most complex functions in the whole reversible ICO. In both of these functions, so all of these functions cannot work if it's not frozen. So it has to be not frozen, and the rICO obviously has to be running. The only time where we allow canceling, even if you're outside, is for the canceling, because there could be the case that you have pending something. The reversible ICO is over. You obviously want to allow these people to get their pending ether out, right? And not say, oh, sorry, it's now ours. So accept contribution. So basically what we have here. Yeah.
Sorry, Fabian, I have a question here. So when you said like this can take up to 600,000 gas, how is that calculated for, you said per participant, right? Is that like, because one of the things that I'm filing is that how many stages do you have in mind? Because someone that is blacklisted, or like anyone, by participating at every stage basically can result in some stock token, right? Like the funds would be stuck because this loop would reach the block gas limit.
So we actually processing per stages, not per contribution. That's why we accumulate whatever contributions to do within one stage. We just increase the pending ether amount in that stage. That's important because, otherwise, if you have to iterate over 100 contributions, that the gas usage could go very high. If you have to iterate over a certain amount of stages, I assume, so this is currently tested with 9 stages. So 9 months, for example.
So 9 is when like the user basically participates in every stage.
If you would participate in contribute something in every state, a very high amount. With the random testing, the highest was ever 600,000 gas. Mm-hmm. And it doesn't matter, if they contribute a lot or contribute 500,000 times.
Yeah, just something, yeah.
Because it's on the end, just processing this amount of ether. So it's just increasing the amount of ether So it should be that max upper bound, depending how many stages you have. So obviously,
so like one of the things I noticed is like even if you blacklist the user, they still can commit further. So like, okay. So sorry, continue. You can.
Yeah, basically everybody is, so there's no real blacklist. Basically everybody is not allowed to contribute until you get whitelisted. That also means that if for whatever reason we reject somebody, he could actually create another pending contribution again. We will probably to reject him again. He could in some way spam us, but we probably will have in our internal systems a max counter. You know, if somebody gets rejected like 10 times, that's it. They can always get the money out themselves. So they can just...
the fact that you pass the array of addresses, like it prevents a lot of attack vectors there that like it doesn't necessarily loop, like you choose like what addresses to loop to. But yeah, that was one of the things I thought.
Exactly. Sure. So basically we probably will do it per address, even though we have an array there. Just for security reason, we will do it per address. And yes, it's not cheap. I mean, I would assume that most contributions will be not more than 1 or 2. But you know, if whatever somebody, I mean, it's also very unlikely that somebody has contributions in every stage, because we definitely cancel him after 2 weeks already. So he will definitely have maximum contributions in 2 stages. But yeah, that's the loop over the stages is definitely a hard limit. But it's per stage. Okay. So basically what we do here is we do basically the same thing. We accept contributions that's either called in the whitelist function or this is called in the commit function. So again, we get the participants' statistics. We check if he has pending ether. If there's no pending ether, we fail silently because we don't want to revert his whitelisting. So somebody can also, you know, first do the KYC, get whitelisted, and then contribute. So contribution can either happen before or after getting whitelisted. It shouldn't be, it shouldn't make a difference when you get whitelisted. So what we then do is basically we get the current stage. We have a variable for the total returned ether and the total new tokens that he gets. So we calculate the participant allocation because we always have to make sure that we know what is this current reserved ether and the unlocked amount, because now the pot will change. There will be something added to the pot, more ether in the pot, more tokens reserved. So we have to calculate before anything else happens. That's exactly the same for the withdraw function as well. What we then do here is we basically have this for loop. In very simple terms, let me first skip that for loop. We have a for loop where we go over all stages or until the current stage. And after that, we send back whatever ether he gets back, which we could not accept. So for example, if there was only 10 tokens to be bought and he sent us ether for 20, then obviously he gets the ether, the overflown ether back for the 10 tokens he couldn't buy because they were not available anymore. So here basically, we simply increase the total returned ether. And we actually count this to the global withdrawn ether statistics, which is something I should actually overthink. It's probably not even necessary. This is only really a visible, like for visibility variable. So here we basically sending back the ether and we call it contribution accepted overflow. So basically when there was a contribution accepted, there was an overflow, there was too much ether sent and we could accept. We send the amount of tokens to the address and we do again sanity check. So the whole magic happens within this for loop. So within the for loop, basically we go over each stage until the current stage. We get the participants' stages struct. We check if there is something pending within this stage. If there's nothing pending, then we skip to the next stage. If there is something pending, we basically get the pending ether here, which we call newly committed ether. We assign this to a new variable because we need to check if it's, we need to basically alter it, and we don't want to alter it on the structs variable. So we have to check how much ether are available or buyable or committable at this stage. So this function basically checks how much the total supply currently is worth in Ether based on the current stage's token price. That gives us the maximum amount of Ether that he could commit. And we then have to check if what he tries to commit is higher than what could be committed, then we basically have to have a return Ether amount or a total return Ether amount. So what he gets back because he couldn't buy tokens for that. And we have to reduce the newly committed or the pending Ether by that amount. So basically we decrease the committed Ether by what's maximum possible, and we just keep the rest in the newly committed. Here, I mean, this is kind of like the tricky things because here we do price calculations. When we go to the committable ETH at stage, basically what it does is just gets the token price, or it just calculates the token price for whatever amount. In this case, we do use token supply. Previously, we actually used the current supply of the reversible ICO itself. We do need to use token supply, a variable, which is always increased when there's tokens added to the rICO and decreased when there's tokens removed. Because in this loop, we have to reduce it. Because obviously, when he like contributes stage 1, 2, 3, 4, 5, he gets, let me move this away. Basically, we have to check for less amounts. So sorry here. Okay, so we are back.
No, actually, like, I had a question. So when on that function, you call this other function that does the real math, like get ETH amount for token at stage. I just want to know, like, what is the formula there that you're using?
So basically, like the token multiplied by the stage price and divided by the token decimals. So to make sure that each token buys at least one way. One way buys at least one part of the tokens.
And the limit on each like stage, I didn't see that. Like where, like, is that defined, or is that like just because of by this math?
So what it does basically, it takes the token total supply. The token total supply is the amount of tokens that this reversible ICO has. This is the total. Let's say there's 10 million tokens left. He has to basically calculate for each stage how much Ether there would be, because we're getting Ether in, and we have to check, you know, is there enough? Can we accept that amount of Ether? So what happens here is, and that's kind of a bit of the magic, is we do this math, and down here we decrease the token supply for whatever amount of tokens he gets. So when he now goes to the next stage, and that is counting from stage 0. So basically we first start to accept the early stages where he participated, and then the later stages. So let's say the token supply is like reduced to everything that could be contributed. So basically people are buying up his like first 3 contributions buying up the whole token supply. Then any later contribution would count is that is 0 times whatever is the token price, 0. So no Ether could be any more committed. And then basically everything else just gets returned, and he cannot commit any more Ether. That's why we have to calculate, like, reduce this here, and cannot go with the actual token balance, because by this point in time, we haven't sent any tokens away from the address. It's just accumulating. And that's actually what happens here. So this function is simply making sure that whatever he wants to buy in Ether in this stage is actually available. If not, we calculate whatever should be returned and whatever he can actually contribute. Then we convert this Ether in tokens. So we get the token amount for Ether at the current stage. We give to whatever Ether he gives, and it gets us the token amount. We these total new tokens, that's kind of what he gets down here. So that's what we will send him. Total new tokens is what he actually will get. Total returned Ether is the actual overflowing Ether amount he will get back. And the rest is really just simply adding. So basically the current reserve tokens get a new extra amount of So they were this calculation. So this variable got basically calculated or recalculated here at this point in time. So we calculated the correct allocation by this point in time for that user, and then we add whatever he got new. So then this is the moment we increase his reserve. We do this for the total reserved amount. So reserve token is basically everything he ever reserved. The committed ether amount for him goes up by his committed ether. The pending ether amount goes down by his committed ether, but also down by the return ether. Because obviously whatever gets processed has to be reduced. And depending, so the same thing happens for the stage itself, and the same thing happens for the global variable. And there was actually one bug where we didn't subtracted the return ether from the global pending, and in certain edge cases you couldn't contribute anymore. Committed ether, same thing. This is just simply updating global variables, and obviously there's new ether committed, which gets added to the project's current reserved ether, which was also calculated in here, the latest state of it. So the most important thing is that always everything has to be calculated before anything gets added or removed. And then it gets added and removed here. So after he has this loop, basically he ends up with two variables. The total return ether, that's basically overflowing ether. He couldn't contribute, and the tokens he gets. And then we do another sanity check. So that's the more complex function. Yeah, in this whole thing. Any questions to that? All right. So the other more complex function is the withdraw function, and the withdraw function is the magic of the rICO giving your money or getting your ether out. And the withdraw function is actually, oh, come on. Oh, sorry. So the withdraw function is actually called in only one place. And this is if you're sending the token back, if it's coming from the project, we increase the supply, how we described. But if it's coming from somebody else, but coming with the right token, the rICO token, then we call in the withdraw function with who sent it and how much token has he sent. And that brings us to the participant address and the return token amount. Again, we check that it's not frozen and it's currently running, because you can only participate when it's running. We get the...
So to that point, so the other function that you just said that it calls the withdraw, it is not checking if it's running, like where this withdraw is called.
That's correct.
Receive tokens? Yeah, just want to know. Oh, you can add to the token supply. Okay, I see.
We need, before the whole thing starts, to add actually some tokens so that they're viable. And because this function does the check, it's not a big deal. Yeah. So basically, we get the participant. So we do two checks. First, is the return token amount larger than 0? So does he even send anything back? You know, I guess the function probably wouldn't be called if he tries to send 0, but you never know whatever people token contracts make. So we do check if there's something sent. We then check also if his current reserved tokens amount, this is the last time we calculated this, was there before we did any calculation, even anything available. And that is something which basically I should probably move below this calculation, because there could be something available, but not anymore. Even though it's very unlikely, because it only is 0 when we are at the end of the reversible ICO. So it could even stay here. But I probably will move this below this function, because the calculation can already happen before. And we check, so basically this is really just a security check. It's a bit unnecessary actually, because we can check the current reserved or the reserved tokens, both of them will likely, so if this is over 0, this is also over 0. But you know, double check is better than one check. So then we do exactly the same thing. So we calculate the allocation by this point in time. Very important, always do the calculation before anything gets changed, because that means from whatever something last time happened, we have to calculate what this guy did. And again, this also calculates the distribution for the project. So it calculates for that person who will change something on his pot and on the global pot, and it calculates for the project so that everybody is basically up to date at this point in time before we withdraw or return anything. So then we basically check, what he wants to return, is it higher than what he even has still reserved, he has available? If so, we do exactly the same thing. We basically have to calculate for an overflowing amount. So basically we have to keep track for the token he sent back that actually are not returnable anymore, because he could have still reserved 10 tokens, but he sends us a transaction with 50, right? That's actually no problem. We only give him the ether back for 10, and he gets to keep his 40 tokens. So it's basically, it's just more convenient this way. We don't do this convenience for the project, even though we could probably do that for the project too. But in this case, we just, you know, let people to send any amount. Otherwise, they're getting confused and have to send specific amounts, which, you know, is hard to do.
But here, if they're reserved, can they transfer that?
So they can, and that's what the rICO token contract protects. They can only to the reversible ICO. They can transfer it only to the reversible ICO. They cannot transfer it anywhere else. And they would be able to transfer it to an address of our choice in the future, because that would be the migration process. So however,
mainly for withdrawals, right?
So basically, they can send it to the rICO and to the migration address. We have to add the migration address allowance too, because the point is that the LUKSO network could start before the rICO is finished, and then people should, even their reserved token, because they are equally counting, they should be able to transfer them or migrate them to the native LUKSO network. The good thing is, in this migration process, they gave them away, so they have no way to refund anything because they're then inaccessible for them as well. So basically, if you migrate to the LUKSO network, you basically fortify your possibility to return your ether. You instantly buy them by that point. So initially, the withdraw function was a lot more complex, but we basically managed, and that is sadly the only way how we could make it possible, to reduce it to this. The rest is really just transferring and again updating variables. Initially, what we wanted to do is basically iterate over your contributions and give back the highest contribution, the one with the highest price. The problem is, as the only math, how this whole thing can work out is based on a total pot size, and the project basically takes always the amount of ether which are by this time rightfully theirs. It basically, what it does, it takes under the hood the average amount of ether price of your tokens. It takes the average price of whatever contributions you ever made. So if we give back, we also have returned the average price of whatever you're getting back. So you basically, what this does, it calculates the average price over your, let's say if you have one contribution, you get exactly the same price back. But if you have one lower and one higher, and you return a certain amount of reserved tokens, it's as if you would give from each contribution a part back. That's kind of how it works. And that's the only way of how you can make this math work out, except somebody wants to show off his math talents in a smart contract and prove us otherwise. So basically what it does is first it checks if we're in stage 0. If we're in stage 0, we're in the commit phase. So you get exactly the amount you put in, obviously, right? And anyways, it's one price across the whole stage, so it makes no difference. But if we're in any of the other stages where this already distribution happened, then we have to calculate, basically, we take the committed ether amount, that's all the ether he ever put in, minus all the ether he ever got out. And we multiply this by the amount of tokens he returned plus the amount of tokens he has reserved. So reserved token is basically the equivalent in tokens to the committed Ether amount. So it's basically all the tokens he ever reserved minus the tokens he ever took out. So every time he reserved more, we increase that. Every time he takes tokens out, we decrease that. These reserved tokens doesn't mean what you have currently reserved and how much you have unlocked. It's basically whatever tokens you ever reserved within this reversible ICO. Same with the committed Ether is whatever you ever committed within this reversible ICO. Not calculating which part you already gave away and which not. And what we do is basically we get the percentage of what you're returning, how much of the reserved tokens you're returning right now. And we can do that because we already check here if it's below the current reserve tokens. So you cannot obviously give more back than you even have still, locked. But here we can simply calculate, okay, let's say it's 1% of whatever you ever reserved, then you get back 1% of your Ether you ever committed, which basically makes it the average price of all your commitments. We have to multiply it by power to 20 in here in order to prevent rounding issues. In the worst case, somebody is giving us or we giving them one way. Probably we get one way extra, let's say. I guess that's a fair thing to do. And after that, we basically increase the statistics. So he has withdrawn now. Oh, sorry. We decrease his current reserved amount, including his total reserved amount. We decrease his committed amount. This is all sub. We increase the token supply. So now there's more tokens to be available again. The withdrawn Ether, obviously there's some Ether withdrawn. There's some committed Ether that is reduced. So that's the total pot size. And importantly, most of these, besides this one, is actually more display functions. But this here, project currently reserved Ether, that's kind of like the current pot size for the projects, from which the project will do calculations again of how much he should have gotten since this point in time, since this withdrawal happened. And obviously there's more Ether. There's Ether reduced because we get Ether back. And then we just do the same thing. We check for the overflow tokens, send him the overflow token amount back, and we send him the Ether back. And we do a sanity check. So that's in the whole, the reversible ICO. Yeah, so that is basically, and to get an overview, basically we have a bunch of view functions. We have these application events defined, which currently is in application types. We might change that. So you have an added contribution canceled and approved. Same with whitelist this listing. You have init functions, and then on the top you have these public ways to interact with it. You have certain functions that are all view functions that give you current states, like how much the project has available, how much the user has unlocked, a specific user, blah, blah, blah. What's the current stage? And here, by the way, is the fix we were talking about. So basically, also nicely, if we are frozen, we return just the freeze start as the current block number because we behave like from this on, the current block didn't move anymore. So that it always shows the current state you're in without that, like now it's showing you higher stages, even though the time is actually not moving. Because the frozen period is only calculated when you unfreeze. And then we just basically, if it's normal, we add the frozen period because we will deduct it down here again, right? So that solves then this whole thing.
Yeah, like to me, it a bit looks like a hacky fix. I may come up with like a better solution. Like one of the suggestions I had in the issue I found was to have, because I know you use the get block number in some functions to get the current block number and some other to get it considering the freezing time. So it might be better to have like another function called get block number deducted frozen, like some kind of namings that it's obvious what's happening. So it wouldn't be a bit this hacky, because like especially like if this rICO would be more framework for others to use, like these fixes might be tricky.
I'm very
yeah.
Absolutely. So this is something. So the thing is, reducing it from the block number is the easiest way to basically make the whole math work out without having to. I mean, another way would be basically take the stage, increase the amount of blocks within that one stage, so that it's still like mapping out. That could be another way. Maybe that's actually even cleaner.
Yeah, like I have to think about it a bit, but it could be easily fixed with a naming function, like a duplicate function that has a naming right, or I have to think about it. But like just this fix seems like to like fix that for now.
Subtraction addition of the frozen period in multiple places, but I'm also want to reduce basically every function that should be visible. In my opinion, should be important, right? And not only for internal use. I mean, otherwise we make it an internal function. But I mean, even thinking about like committable ether at stage, I mean, it is a nice function because it could be interesting to even like show in an interface, hey, that's the maximum amount you can send right now, right? I guess that's definitely important to have. So most of these functions, the public view functions, are there because they are somehow relevant to an interface. Yeah, and then we basically have the internal function, which really do the allocations and the processes. And there's only these three processes, either canceling something, accepting a contribution, or multiple contributions in this case. So either you cancel all contributions or you accept all contributions. That's just kind of like the two ways. Or you withdraw from your reserve tokens. That's basically all there is. Is there proof, like, is there room for improvement? Maybe. We have already like reduced that code by a lot. That was a lot more complex in the past. Do we need all of these functions? Sadly, most of them we do. Even though they are the ones which are the most expensive in terms of gas cost. We did some testing in terms of contributions. So a normal contribution costs you around 180,000 gas. If you're not whitelisted and you just make a pending contribution, they cost you 80,000, 60,000 gas. So that's cheap. But on the end, we have to bear the cost of giving you the tokens. So, but the first contribution in any case will be 100 to 200,000 gas because it will create the user in that sense. Yeah, that's basically all there is to say about the code.
Yeah, thanks. But by the way, just like I'm really enjoying reading this code because like the comments